In this lesson, we're going to talk about hypotheses and simulations. So basically, how can we run a simulation to test a hypothesis? And when we talk about a simulation, it doesn't necessarily mean we're actually doing whatever it is we're trying to simulate, but we create a kind of similar situation where we can get outcomes from what we're trying to test, if that makes sense. So let's go ahead and run through an example. So if you look at this hypothesis, Mrs. LaRocca claims that she's great at basketball and that she can make a free throw 4 out of 6 times. So this is key right here. She's saying she's great because she can make a free throw 4 out of 6 times. So if we want to simulate this without actually having to go out and get a basketball and actually shoot those hoops, we can think, okay, well, what has 6 possible outcomes? Oops. So we need something that can simulate 6 possible outcomes, equally likely outcomes, 4 of which, right, you can make the basket, and 2 means she doesn't, she misses. So something very common we can use that simulates 6 different outcomes is a dice. Okay, so we can roll a dice because it has faces 1 through 6, and then we can define it saying, okay, we want 4 results. That will be, yes, she made it, 1, 2, 3, 4, right? 2 results saying she didn't make it, we'll say that's 5 and 6. It doesn't matter if you wanted it to be, 1, 3, 4, and 6, that was, she made it, and the other 2 she didn't, just divvy it up. So you have 4 that represents a success, and 2 represents a miss, okay? And then we can do the simulation by rolling dice, and obviously you can't see me roll any dice right now. So I'll just go ahead and give you the results that we got. So the first roll was a 4. Is that a success or failure? Well, that is a success. I'll use S for success. Roll 2 was a 5. Is that a success or failure? That is a failure. All right. And so on. So we can say roll 3 ended up being a 3. Awesome. That's a success. And then roll 4 was a 3. That's a success. Roll 5 is a 1. That is a success. 2, roll 6. That's a success. 7 was a 6, and we're like, okay, 5 or 6 is a failure, so that's an F. 4 for roll 8, that's a success. 9 was a 5, which didn't work out. And then the last roll that I rolled was also a 5, which is a failure. So we had 6 equally likely outcomes, 1 through 6, to simulate these 6 different outcomes of Mrs. LaRocca making the basket, right? 4, 1 through 4 are success. 2, 5, and 6 are failures. Okay, so obviously we don't want to just trust one simulation. So what we want to do is simulate this multiple times. And the more you do it, the more, I think, confidence you can have in your data. So if we were actually in class, I would have you guys take out a dice and start rolling yourself. But before we do that, I should mention, we don't want to just look at these numbers as it is. We want to talk about the proportion of successes. So we want to think about, okay, what basic percentage, or I should say probability, right, from our experiment gives us a success. So we had how many successes here? 1, 2, 3, 4, 5, 6 out of 10 were successful. So the proportion, 6/10, is equal to 0.6. So that's what we use here. So we're saying our proportion is 6/10 or 0.6. That will be successful. All right. So now going back to this, if we were actually in class, I would totally have you guys bust out dice and roll the dice on your own. But since you're not here and we're doing this virtually, I'm just going to go ahead and give you information from last year's data. So I'm actually going to go ahead and give you the proportion. So you can imagine this is just saying how many successes we had out of 10. So the first student last year had 0.6, which means they also got 6 successes out of 10. The second student also got a 0.6. Then the next one got a 0.5, which means 5 out of their 10 were 1 through 4. All right. The fourth kid got success, 0.6 out of 10. Then we have a 0.5. Then a 0.6 and a 0.7. That means 7 out of 10 were 1 through 4. And this one was amazing. They got 100%, 1 through 4, then 0.6, 0.4, 0.4, 0.7, 0.7, 0.5, 0.5, 0.9, and 0.6. So you can see the more we do this, the more you'll kind of get a better sense of what the spread is of the possibilities. And if you remember from the last video, we want to create a histogram to help us visualize, right? What is more likely to occur by chance, which would help us kind of determine the hypothesis is probably true, versus something that is completely not really a chance situation, which would mean the hypothesis is false. So we want to create a histogram. All right, so our data is right here. We're going to use the data that I have right here in the table. And we want to be careful because we don't want to just, plot 0.6 and count all that. What we want to do is we actually want to calculate what's called the relative frequency. And what is relative frequency? Well, this is kind of a way for us to see out of like 1 or 100% how often this outcome happened. So how often did we get 0.6? How often did we get 1? And things like that. And let me actually just rewrite my axis because that's a little hard to read. There you go. So how do we calculate the relative frequency based off of our raw data, which is, right, the proportion of 10 rolls that result in a free throw? Well, in order to do that, all we really do is just take the kind of tally, the frequency of how often we got that proportion and divide it by the total. So basically we're just creating another fraction. So what you can do with this is, if you'd like, you can make a little table, which I will try to fit in right here. So we can have the proportion that we calculated, and then we want to know its actual frequency. So did we get it once, twice, 15 times, whatever, right? And then what we are going to do is take the frequency divided by the total. Sorry, that's really hard to read, but again, that's frequency divided by total. So let me show you the first one, and then I'll just show you the completed table. So what you might want to do before you start just putting the proportions on here is maybe look at your overall spread of values and just go least to greatest, because that's how we're going to put it onto our histogram anyway. So 0.4, and then I can see we have a 0.5, 0.6, 0.7, 0.9, and 1. So I'm just looking from least to greatest just to organize that. And again, let me just show you this first one, and then I'll show you the completed table. So 0.4 appeared 2 times in our entire set of data. So that means the frequency here is 2. And again, you can tally or you can just write down that number. So how do we find the relative frequency? Because that's what we're looking for here. Right, this is relative frequency. Oops, I should maybe point to this entire table is calculating relative frequency for each proportion. So then we're just going to out of how many total trials we had. So we had a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, right? So if you count up all those different numbers in that chart or in that grid, we have a total of 17. So that's my frequency over total, which is my relative frequency. Okay, and then to make it a little bit easier to graph, I'm just going to scoot this over a little bit. Let's go ahead and round that to the nearest 10th or 100th. So that's approximately 0.12. Okay, so we can go ahead and do that for every single one of the proportions we calculated from our 17 different simulations and get that relative frequency, which is that frequency over total. So I'll show you the completed table. And there we go. So that's what we're going to go ahead and use to graph. So what we're going to do is basically put the proportion on the X, like I had labeled on my grid here, and then the relative frequency here, these decimal values, as our Y. So you want to go ahead and determine your scale to try to fit all of the bars in nice and neatly and make it hopefully pretty straightforward to read. So you can figure out your scale if you'd like, but here is what I'm going to do. So you can see to make it fit from 0 to 1, I didn't quite have enough tick marks on the x-axis, so I just went ahead and went by 0.1. And then on the y, it's okay if you need to extend that a little bit. If you're doing your own work, you can definitely feel free to use your own graph paper so you can make your grid as big or as small as you would like. But I think it's kind of nice to use intervals that are easier to count. So I could have fit everything in if I went by 0.03 or 0.033, I guess 1/3 in that sense, but it's a little bit harder, I think, for readers to kind of estimate or figure out what that value is. So it's usually nice to go by 1s or 2s or 5s or something very reader friendly. So just a heads up there. So I decided to go by 0.02 to count by 2s to make it all fit. So I just had to add in 3 extra tick marks so I can make this go up to 0.36 to fit in that 0.35. Okay, so just like with other histograms that we've done before, hopefully you're using your straight edge, but I'm going to freehand this because I'm using my tablet. We're going to just go ahead and draw our bars. And basically, for anything we don't have a proportion for, just leave it blank. So I'm not going to draw anything for, from 0 to 0.1 or 0.1 to 0.2. I'm going to start here at 0.4. And between 0.4 and 0.5, right, we have 0.12. So that's going to be right here. So that's my first bar. Then our next bar from 0.5 to 0.6, we have 0.24. So that's going to be up to here. Then from 0.6 to 0.7, it's 0.35. So that's the one I have to kind of get all the way up here for and go between those last 2 tick marks to get that 0.35. And again, hopefully yours is much nicer than mine because I'm freehanding this. From 0.6 to 0.7, it's 0.18. 0.7 to 0.8. Oh, that's the one I already did, sorry. Then you'll notice we have a gap. We don't have anything from 0.7 to 0.8, so we're going to leave that blank. And we'll just start up here from 0.9 to 1. So that's 0.06, which is here. Oops, and that one's a little bit off. So 0.06 once again is here. And that's the same value for 1. So you can see how it's perfectly fine to have a gap because we just don't have any data value. We just have a flat bar. It doesn't actually rise from the x-axis. Okay, so that is our histogram. I'm going to kind of scoot this over so you can read the data. And let me jump down to the hypothesis analysis, and then we'll talk about other ways of collecting data for simulation. But based on that histogram, right, is her hypothesis true? So we said she only makes 2 out of 10. So 2 out of 10 as a proportion is 0.2. If we look back at our histogram, we've got nothing at 0.2. So it's highly unlikely that that happened by chance. It's highly likely that is Mrs. LaRocca's real skill, which unfortunately means it's not that great at basketball, right? So this is no, right? So I just switched over to typing because I figured it would be a little bit easier for you to read. But again, it didn't occur in the simulation, so it's highly unlikely to occur by chance. So very doubtful that her hypothesis is actually true, right? Okay, so going back up to the question, besides rolling dice, or the comment here, besides rolling dice, other ways to collect data for a simulation are, and like I said, the simulation doesn't actually have to be the activity. We're not going out and, throwing baskets. We used a dice based on her information saying, okay, she can make the baskets for the free throw 4 out of 10 times. So we use that to create a simulation. So as long as you have something like that to work with, if you want to do something like with a 50-50, we can, chance happening one or the other, we can use a coin toss, right? If we have more outcomes, we can use like a random number generator on your computer or your calculator. We can pull numbers out of a hat, right? So we can just run a very basic simulation as long as we have some guiding information, okay? And again, dice, a very common one. And we have different sides, a different number of faces on dice, right? We have standard one, 6 faces, but you can have up to 20 or more. So you just really have to think about what the situation is telling you. So let me go ahead and write all that down for you. All right, and there you go. And again, those are just some examples. There could be much more out there. Maybe you'll come up with a new one that's kind of cool to work with. But again, these don't have to be crazy difficult to work with, like just rolling a dice, but it simulates the outcomes. That's what's important. All right, so let's move on and let's talk a little bit more about what we can interpret from these simulations. So if we look at the next example, a national polling company claims 34% of US adults say mathematics is the most valuable school subject in their lives. And then you're going to survey a random sample of 50 adults. And what we can do is we can first do a simulation and then compare that with the sample to kind of see or get a feeling about how accurate the claim from the polling company is. So if you look here on the side, there's a description about how the simulation was done. So if you just kind of read through that, hopefully you understand what's going on here. We're simulating and picking 80 random samples of size 50 using a random number generator on a graphing calculator. Now, why is it 80? It's not like there's some magic number. Like I said, the more simulation trials you do, the more confidence you would probably have in your simulation. But like I said, is there a hard, fast number? You have to do 80 every time? No, maybe if you had time, you can do 800, right? So for some reason, this person, when they simulated, they did 80, and they thought that would be enough to give them confidence in their simulation. So that's what we want to think about, okay? So using a random number generator, so on your graphing calculator or on a computer, you can just pull numbers out of a hat as well, but you're just randomly generating numbers, and this person decided to use your graphing calculator. And they decided to do numbers from 0 to 99. And why is it not 1 to 100? Beats me. You just need 100 numbers. Why is it 100 numbers? Because if you're thinking about percentages, 34% is 34 out of 100, right? Because it's 34 divided by 100. So we know if their claim says 34% of the US adults will say math is the most valuable subject in school, then 34 out of 100 numbers should represent the people who say, yes, math is valuable. And then the other remaining 66 would be the ones who said no. So you just basically have to pick your band. This person decided to pick 0 to 99 to get a total of 100 numbers, saying 1 to 34 said, yes, math is the most valuable. And then 0 and 35 to 99 said no. You could have done 1 to 34 and then 35 to 100. It doesn't matter. You just need to have 100 numbers, if that makes sense. Okay, so the results are here in the dot plot on the left. And what we want to do is, if you look below, we've got some questions to help us analyze the claim with our simulation. So if you look at the question here, what can you conclude about the accuracy of the claim that the population proportion is 0.34? So that's just converting, right, the 34 over 100 to the proportion. So we want to compare that with our survey data. So our survey that we ran said 15 out of 50, because you can see, right, that's what we said we were surveying. We're surveying 50 adults. So 15 out of 50 in our personal survey, where we actually went out and talked to people, said math is the most valuable subject. And again, assuming that our survey was unbiased and completely random and all that. Okay, so how do we analyze this? Well, let's first see, okay, let's look at our data. This 15 out of 50 is 0.3. So we can see right here, 15 out of 50, 0.3 occurred this many times. So it occurs 7 out of 80 times. Right, so it occurred 7 out of 80 times. And we're not actually going to do anything with that number. We don't need to find the probability or anything like that. But what we want to see is it did occur, and it occurred more than once. So is that likely or highly unlikely? And because it occurred multiple times out of our 80 trials in our simulation, we can say, well, yeah, it did happen. So it's likely that the claim is accurate, but can we say with 100% certainty it's accurate? No. So what we're doing is we're basically just assessing how probable, right, the claim is accurate or not accurate based on our simulation. So to the best of our ability, we can say, yeah, it's likely that does happen, but are we 100% sure? No. Okay, so that's what we're basically saying here. So I just want to emphasize again, it's important to note we're working on that population percentage or that proportion of 34% or 0.34. So this would be a totally different conclusion if the polling company had claimed, 75% of US adults say math is the most valuable school subject. So just make sure you're really clear about what the kind of conditions are in our conclusions that we base our conclusions off of. Okay, so if we look at the second question, what if we went out and polled again, and let's say now instead we had 25 of our 50 said math is the most important subject. So now instead of having 15, we've got 25 now. So we have 25 out of 50, which is now 0.5. So you can see here, and I'll highlight this one in a different color, we've got this 25 out of 50 right over here. So on the right. So then we want to judge based on that dot plot how likely it is that it occurred. Well, you see that it only occurred once out of our 80 trials. So that being said, yes, it did occur, but it didn't occur very frequently, right? Compared to that 7 out of 80 earlier. So only showing up once makes it more unlikely for that to actually happen. So now, again, to the best of our ability, we're not saying definitively yes or no, but we're saying this is less likely to happen because it's just not very probable. 1 out of 80 is kind of a stretch, right? It could be something that happens very, very infrequently. So we don't want to say that, it's likely that 25 out of our 50 adults would say math is the most valuable subject using the 34% population proportion. So the claim is not accurate. All right. So again, very unlikely that we would actually have 50% of our survey, right? Surveyed people say that they think math is the most important subject if the percentage that we're using is 34%. So we're going to say, I shouldn't say it's not accurate, but probably not accurate. Likely that it's not accurate, because again, we don't want to say anything definitively. Okay, so next, just a short you-try problem for you guys to also kind of analyze this simulation and the claim here that 28% of US adults say students should be required to participate in PE every day. So again, use that simulation and the percentage to kind of base your conclusion on. So you're telling me if the claim is probably accurate or probably not accurate. Again, make sure you're using that keyword probably, because we don't want to say anything with certainty. And here are the answers. So, oops, I forgot to tell you to pause, but hopefully you remember to pause to try out those you-try problems. But again, if you just counted up the dots, you'll see we had 70 trials for this simulation, and we're just using the claim, right, or the survey information to analyze the claim. So with the first one, 5 out of 70 times we had in the simulation 16 adults saying that PE should be a daily requirement. So it's not a small number. It's not like 100% of the data, so we can't say it's incredibly likely, but we can say it's likely, versus the second question where it only showed up twice out of 70, which is much more infrequent, even though you might be saying, well, 2 is not that much lower than 5, but 2 out of 70 versus 5 out of 70 is actually, I think, decently significant. So you can see it's much less likely for 21 adults to say that PE should be a daily requirement. So we're going to say that claim is probably not accurate. And again, make sure you have probably in there because we don't have absolute certainty about any of our conclusions. Okay, so that wraps up hypotheses and simulations. Please let me know if you have any questions, and as always, thank you for listening.